First I'd like to thank the organizers for giving me this opportunity to speak in a very nice conference in a nice place. So in this talk, I plan to talk about the topological protection and planar Hall effect. This is about 3D TI, and also topological superconductivity in copper bismuth selenide. And I'm going to show you some of our recent efforts that we are doing at Köln. And my work has been supported by Köln CRC as well as recent advanced ERC advanced grant. Yeah. And I have been in Köln for already 2 years, and my group has grown reasonably big. So now there are about 12 people, 6 postdocs, 5 PhD students, and 1 master student. Yeah. And for theory, I'm enjoying a discussion with Achim Roche and also Alex Altland. And for fabrication, which I'm going to show you today, but done in collaboration with Professor Matsumoto at Osaka, but in Köln, we are now building our own clean room. And for the topological superconductivity in copper bismuth selenide, we've been collaborating with Professor James' group for NMR and also with Professor Maino's group for magnetocaloric measurement. Yeah. So I'm going to skip all the introduction and go directly to topological protection. So you know this topological surface state, which has a spin momentum locked nature. And this nature means that wherever the chemical potential is located, plus k electron cannot be scattered back to minus k electronic state because of the spin mismatch. And this is the protection from backscattering, which makes the mobility of the surface state to be, in principle, relatively high. Yeah. But this protection can be lifted when a gap opens at the Dirac point. And it has been already demonstrated, for example, that the surface state at the top and bottom are hybridized when the thin film becomes very thin. Then the gap opens at the Dirac point, and this gap opening or the hybridization between the top and bottom surfaces lifts the topological protection. And this is a plot of the surface conduction, a ratio of the surface conductance to the total conductance versus the film thickness. Down to something like 8 nanometer, the topological surface state is kept intact. But below 8 nanometer, they start to hybridize. And once such hybridization occurs, the surface conductance gets plumbed. And this is due to the gap opening. Yeah. So in ultra-thin films, the topological protection is lifted. And also, as you know well, the quantum anomalous Hall effect is kind of a breaking of the topological protection. So in this case, we introduce ferromagnetism in the topological insulator thin film. And this ferromagnetism leads to the gap opening at the Dirac point. And when we can tune the chemical potential into this gap, then the 2D bulk or the 3D bulk becomes insulator, and we are left with the chiral edge state. And that leads us to observe the quantum anomalous Hall effect. And this is a lifting of the topological protection due to the perpendicular magnetic field or magnetization. Okay. And so far, it has not been so well understood what the effect of the parallel magnetic field for the time reversal, about its time reversal breaking effect. Yeah. So parallel magnetic field is naturally breaking time reversal symmetry, but to first order, its effect on the Dirac system is negligible because the magnetic field couples directly with the Pauli matrices. So this k dot sigma is transformed into this one. So this Dirac Hamiltonian, in the presence of magnetic field, is transformed into this form. So the z-axis magnetic field opens the mass gap, but the in-plane magnetic field component only shifts the Dirac point. Yeah. So when the magnetic field is applied in plane direction, then it just leads to a shift of the Dirac point. Okay. And such a shift in the Dirac point can be easily gauged out by just shifting the origin, and all the transport calculation is done by taking the band bottom as the momentum 0 point. So this renormalization is typically done. So for as long as the transport properties are concerned, this parallel magnetic field should not have any effect. But we have come to find that the in-plane magnetic field actually has an observable effect on the surface transport properties. And that happened in the so-called Planar Hall effect. And to explain you about the planar Hall effect, I should start from the basics. Although many of the audience are already familiar with this effect because they are specialists on ferromagnets. Okay. So when the system has a anisotropic resistivity tensor like this, any anisotropic resistivity tensor can be diagonalized by taking the principal axis along the anisotropy axis. But when the frame of the measurement or direction of the current is not along this principal axis, then we need to introduce such a rotation of the frame, and that leads to the appearance of the transverse voltage, even when only the current is applied along the x direction. So this longitudinal voltage is called angular magnetic resistance, and the transverse voltage occurring along the Jx component is called the planar Hall effect. And it is well known that in the ferromagnetic system, the appearance of the magnetization leads to the anisotropy in the resistivity tensor, and the resistivity is always larger along the magnetization direction compared to the perpendicular direction. And this anisotropy axis rotates together with the magnetization axis. But when we keep the frame of the measurement to be constant, then there is a change in the angle between the frame of measurement and the frame of the principal axis. And this finite angle between the two frames leads to the appearance of both the anomalous magnetic resistance and the planar Hall effect. And these components are nothing but this matrix component, which shows up as a result of the rotation of the frame. And we have come to observe such a planar Hall effect and the anomalous Hall effect in the bulk insulating topological insulator thin film. And this is the data for the planar Hall effect signal and the angular magnetic resistance signal, which follows exactly what has been known for the ferromagnet. And this essentially means that the magnetic field induces some resistivity anisotropy in the resistivity tensor in the surface state. And this is the angular dependence of the planar Hall signal. And this inset shows the magnetic field dependence. And as you can see, that this planar Hall effect signal is always symmetric with respect to the magnetic field. This is fundamentally different from the usual Hall effect signal. In the case of Hall effect, the signal is always anti-symmetric with respect to the magnetic field. So by judging looking at the magnetic field dependence, we can judge whether the signal which is showing up transverse to the current direction is a genuine Hall effect or due to the planar Hall effect. And in the case of planar Hall effect, it is symmetric. Okay? Yeah. And we have been able to make a device on which both the top surface and the bottom surface can be gated, so that we can control the chemical potential of the top surface and the bottom surface independently. This is dual gating. And this is the gate voltage dependence of the resistivity, longitudinal resistivity, and this is the gate voltage dependence of the Hall resistivity. And you can see when we tune both the chemical potential of the top surface and the bottom surface exactly at the Dirac point, then, for example, the Hall resistance shows a very sharp change from negative to positive, which means that the Dirac point is swept across the Dirac point at the top and the bottom surfaces simultaneously. And at the same time, we see a very sharp peak in the resistivity. This is also an indication that the carrier density goes through a minimum at a well-defined point. And these 2D color mapping showing how this resistivity or the Hall resistivity changes when we scan the bottom gate voltage and the top gate voltage independently. Okay. And for example, this dark red color signifies the maximum in the resistivity. So this maximum occurs in a very narrow region of the back gate and bottom gate plane, which means that the crossing of the Dirac point occurs only at the very well-defined gate voltage. And this capability of controlling the chemical potential of the two surfaces allows us to trace how exactly the planar Hall effect signal changes as a function of the chemical potential. And this is a plot of the amplitude. Amplitude is essentially this. So when we rotate the magnetic field direction, it oscillates, and this oscillation amplitude is plotted as a function of the gate voltage. So this essentially shows how the size of the Planar Hall effect changes as we scan the chemical potential across the Dirac point. And this dotted line marks the gate voltage, which gives us the Dirac point direction, because the Hall coefficient shows a sign change. Okay. And you can see that somehow the Planar Hall effect amplitude shows a double peak structure, and the minimum is lying relatively close to the Dirac point crossing. This was rather puzzling to us, and we tried to scan the gate voltage along various paths in this bottom gate voltage versus top gate voltage 2D plane. And we found that this double peak structure is always there, and it tracks the position of the Dirac point. So this double peak structure is always associated with the Dirac point. So we wanted to understand this. So we teamed up with Achim Roche's group, and he has a very good PhD student who calculated the transport properties in the presence of the impurity and also the in-plane magnetic field. And this is their model. So this is a simple topological surface state. This H alpha beta is the Dirac Hamiltonian. And they consider the impurity state. Impurity state is just has a resonance energy. And this resonance energy can be off the Dirac point. So it can introduce some anisotropy. Okay. And also the impurity couples with the magnetic field just with the Zeeman term. And we also need to consider the hybridization between the impurity state and the surface electron. And after some calculations, they come up with the prediction that there should be anisotropy between the current direction parallel and perpendicular to the magnetic field. And the physical origin of this anisotropy is this. So because the non-magnetic, even the non-magnetic impurities will be spin polarized in the presence of this magnetic field, they can introduce the off-diagonal component between the upspin and downspin. Okay. So when the magnetic field direction is perpendicular to the original orientation of the electron spins, then the backscattering is allowed. Okay. But when the original electron spin orientation is parallel to the magnetic field, then the backscattering is still kept prohibited. Okay. So this introduces, so essentially the in-plane magnetic field introduces anisotropic opening or lifting of the topological protection. And that leads to the anisotropic resistance. And this calculation considers a realistic distribution of this resonance energy. Okay. And so the spin polarization of the magnetic impurities leads to anisotropic scattering. And the theoretical calculation actually coincides reasonably well with what we actually observed. And this anisotropy between the electron and Hall side is most likely due to the resonance energy of the impurity to be located on the electron side. Yeah. So this seems to give evidence for the anisotropic lifting of the topological protection. And furthermore, this theory gave us some opportunities to analyze the quantitative nature of the scattering. For example, the position of the peak, which is a measure of this resonance energy as well as the strength of the scattering, allows us to estimate the mean free path to be 7 nanometer. And also the amplitude of the Planar Hall effect is a measure of the strength of this Zeeman energy, which is proportional to this phase scattering length. So we estimated, based on this amplitude, this phase scattering length to be something like 70 nanometer. So this theory is quite useful, not only for understanding the effect of the in-plane magnetic field, but also to understand the microscopic parameters of the imprinting scattering transport properties. Yeah. So that's about the 3D TI. Then let me switch to topological superconductor. Yeah. Well, I have recently wrote a review on the topological insulator. This is a very pedagogical review, starting from the basics of superconductivity or the theory of topological superconductor, blah, blah, blah. And that was just published in reports in Progress in Physics. So anyone who wants to study, particularly the students, are encouraged to read this review. And I give you a brief introduction of the topological superconductor. So as already discussed during this workshop, there has been already a periodic table of topological invariant expected for topological superconductor. So essentially, a superconductor has a Bogoliubov-Dijan symmetry, which means particle-Hall symmetry. And depending on whether the system preserves the time reversal symmetry or breaks the time reversal symmetry, the expected topological invariants are different. And for example, the proximity-induced superconductivity in the TI surface state to produce the Majorana zero mode or the chiral P-wave belong to this time reversal breaking 2D case. And people are pursuing the possible Majorana fermions using this platform. And also, this 1D time reversal breaking platform corresponds to the well-known Kitaev model, and the 1D spin orbit coupled semiconductor nanowire is expected to realize this topological superconductivity, and there are promising evidence already for the existence of the 1D time reversal breaking topological superconductivity. And in this table, you can see that here, for the 3D system, even though the time reversal breaking 3D superconductor should not exist, a topological superconductor should not exist, a time reversal invariant topological superconductor can exist. And if such a superconductor is found, then it is associated with the helical Majorana fermions on the surface, which will be a new type of exotic quasi-particle and would be quite interesting. And the candidate material to realize such a time reversal invariant 3D topological superconducting state has been this material, copper bismuth selenide. And the reason that this material is a promising candidate is the following. So this is a normal state Hamiltonian of bismuth selenide. And this Hamiltonian is essentially a gapped 3D Dirac Hamiltonian with the four component basis of these wave functions, which comes from the two different selenium orbitals at the top and bottom of a quintuple layer. And the important point is that these two different selenium orbitals have opposite parity. Okay. So since these basis wave functions have opposite parity, it is conceivable that if the pairing occurs between orbitals having opposite parity, then the resulting Cooper pairs will also have opposite odd parity. Okay? And such an odd parity superconductivity is almost guaranteed to be topological. Particularly in this case, the film surface is surrounding a simple gamma point. Okay? And this possibility was first pointed out by Hu and Belk back in 2010. And they predicted that if such a bulk topological superconductivity is realized, then there should be a surface helical Majorana fermions. And they also performed the symmetry analysis of the possible superconducting states, and they showed that based on the irreducible representation of the D3D symmetry of this system, there can be only 4 types of gap functions. And all the 3 unconventional possibilities are topological. And there remains a possibility of BCS type conventional S-wave superconductivity. But even in this case, since this copper bismuth selenide is essentially a doped topological insulator, it has a topological surface state. And this topological surface state can obtain a proximity-induced superconductivity and gapped. And if this happens, then we can expect the Majorana zero mode in the vortex core according to the original Fouquet proposal, or according to more recent calculation by Hossur et al. Yeah. So this material is quite promising. Yeah. So we have grown high-quality single crystals of this system and performed the point contact spectroscopy to prove the possible existence of this surface state. And the spectra we obtained using the point contact spectroscopy is something like this. And the essential feature is that the differential conductance as a function of the bias voltage shows a peak at zero bias and shows a clear dip at the energy scale, which corresponds to the gap, superconducting gap. And this is quite opposite to what one would normally observe in the BCS superconductor. So this is our experiment on the BCS superconductor team. So in the case of BCS superconductor, usually there's a dip in the differential conductance at the zero bias, and instead there should be a peak at the 2 delta energy scale. And these peaks are due to the Andreev reflection, which means that the incoming electron is carried out by 2 electrons forming a Cooper pair. Oh, already 5 minutes? Okay, yeah. So the conductivity is naturally enhanced due to the Andreev reflection process. But when there's an Andreev bound state at the surface, then the conductance at the surface is expected to be reduced. And actually, the theoretical calculation for the point contact spectra expected for this kappa-bismuth selenide material predicts a spectra like this. And this is in good agreement what we have observed. So this zero bias conductance peak seems to be due to helical minor fermions. But for this system, the surface sensitive experiment has been rather controversial because of the difficulty in preparing samples. So to elucidate the real nature of the superconductivity, bulk measurement were really called for. And that's why the NMR experiment was quite important. So my collaborator at Okaima University has measured the spin susceptibility or the night shift of this material. And they applied the magnetic field along the in-plane direction, and they found that depending on the orientation of the in-plane field, the night shift is actually shows a difference below TC. Okay. And this is the temperature dependence. So above TC, the night shift is completely isotropic. But below TC, the night shift starts to show larger dip along a particular orientation and smaller dip along different orientation. And this is angular dependence. And you can see that this particular dip occurs at every 180 degrees, which means it is 2-fold symmetric. But the basic crystal lattice is 3-fold symmetric. So this 2-fold symmetry cannot be due to the lattice, and it must be due to the electron self-organization. Yeah. So this 2-fold symmetric night shift shows that the spin rotation symmetry is spontaneously broken. And this is only possible for the spin triplet state. And furthermore, Minos group measured the specific heat in the in-plane magnetic field. Okay? And they again rotated the magnetic field and measured the change of the specific heat. And the specific heat shows also oscillation, and this dip occurs again every 180 degrees. And this is the plot, a polar plot, which clearly shows the 2-fold symmetry. And they also measured the HC2 as a function of angle, and HC2 also shows similar 2-fold symmetry. And these specific data indicate that the amplitude of the superconducting gap actually has a 2-fold symmetry. So it has this kind of gap structure. And among the possible gap functions predicted for kappa-bismuth selenide, only this so-called delta 4y gap is consistent with the observed NMR and the specific heat. And this delta 4 state is actually characterized by the nematic order parameter according to Liang Fu. And he called it nematic superconductivity. Yeah. So these bulk measurement gives evidence for the nematic superconductivity, which is necessarily topological because it belongs to this delta 4 case. Yeah. And there's a reason why this delta 4 state is preferred, because in the kappa-bismuth selenide system, there is a so-called trigonal warping term as a higher order term. And this trigonal warping term actually prefers or induces a slight z component in the spin, and this slight z component prefers this delta 4 symmetry. Yeah. And we have also synthesized related materials, this natural heterostructural material, and intercalated kappa, and we were able to induce superconductivity. And in this material, we start to see that the specific heat gives evidence for line loss, because the finite specific heat remains down to lower temperature than is expected for BCS, and also the specific heat jump at TC is much smaller than the BCS case. And furthermore, the magnetic field dependence of the lowest temperature specific heat shows a well-known Bolvik effect, which is expected for the existence of the line loss. Okay. Yeah. And so the specific data of this related material, heterostructure including bismuth selenide layer, shows quite unusual nodal gap superconductivity. Okay. And if we remember that this delta 4 gap has this nodal structure, our data actually is consistent with observation in kappa bismuth selenide. So it seems that the nematic superconductivity or the delta 4 state is almost universally realized when we dope electrons into bismuth selenide. And recent experiments on strontium doped bismuth selenide or niobium doped bismuth selenide both showed evidence for the 2-4 symmetry in the HC2 behavior. So it's the realization of the delta 4 state in the bismuth selenide-based superconductors is becoming more and more sure, I think. Yeah. So I'm going to briefly show you the recent efforts. Okay. So in Cologne, the university was kind enough, to build a make a building, and in here we have our MV room or the clean room and the measurement room. So we are now able to do the synthesis, fabrication, and measurement, the complete cycle. And we have been, for example, making the Josephson junction based on topological insulators. And we are also using the bulk insulating topological insulator samples to find better evidence for the topological nature. And in near future, we are planning to make such kind of asymmetric suite to directly measure the current phase relationship. And also, we are measuring nanowires of topological superconductor candidate material. And the result of this nanowire will be shown in the poster session with my collaborator, Fan Yang. Okay. And we will eventually make this kind of Majorana teleportation experiment. And recently, we have proposed a Majorana surface code structure together with Alex Altran and Ryan Hodega. So thank you for your attention.